The last thing we need to cover when it comes to wave are beats. And no, these are not the Beats headphones. All a beat is, it's a distinctive sound pattern due to the superposition of two sound waves of slightly different frequency. The ear is going to hear a single tone that is modulated, and that's going to determine the pitch. And I will play for you what a beat sounds like at different beat frequencies. Beat frequency is extremely easy to find. It's just the difference between two frequencies that differ slightly. So beat frequency is going to be the absolute value of F2 minus F1. And it doesn't matter which one you're subtracting from which because it's the absolute value. So you have two frequencies that are slightly different. You subtract them, that will give you your beat frequency. And then this is going to determine the frequency of modulations. If you see anything asking for beat period, it's just the inverse of beat frequency. So period for a beat is just equal to 1 over the frequency for a beat. Let's just do an example, and that's really all you need to know for beats. So here's a quick example. You hear 2 beats per second when two sound sources, which are both at rest, play simultaneously. The beats are going to disappear if source 2 moves towards you while source 1 remains at rest. So this is combining the Doppler effect. The frequency of source 1 is 500 hertz. What is the frequency of source 2? So we know that F1 equals 500 hertz, and we know that F1 is also at rest. So V1 equals 0. We know that F2 is equal to either 500 hertz plus or minus 2 hertz because you hear 2 beats. So I could add that the beat frequency equals 2 hertz. So that means that the frequency of source 2 is either 498 hertz or 502 hertz. How do we know which one it is? Source 2 is moving toward you. If you remember with the Doppler effect, as something gets closer, the frequency will increase. So frequency of source 2 plus 2 hertz equals 500 hertz. So that means the frequency of source 2 must be equal to 498 hertz. Again, my clue here was the fact that source 2 moved towards us, so that means frequency had to increase so that you were hearing no more beats. So in order to increase and get to 500 hertz, you needed the lower number. Let's do one more example, a little bit more involved. And this tells us a police radar sends out microwaves at 10.5 gigahertz. And just so you know, giga refers to 10 to the 9th. The unit combines the wave reflected from a car with the original signal and determines the beat frequency. The beat frequency is then converted into a speed, and this is how cops can tell whether or not you're speeding with a radar gun. If a car is moving at 20 meters per second toward the detector, what will be the measured beat frequency? So here we have our radar gun. I guess they usually have more of a cone. And it's at rest. And it's sending out waves, microwaves. And then we have a car moving at 20 meters per second toward the detector. If I list what we know that the frequency of the source is 10.5 times 10 to the 9th hertz. Again, that's what the giga stands for. We know that the velocity of the detector, so the car, it's moving toward the cop car, so it would be a positive 20 meters per second. What we're looking for in the end is the beat frequency. So in other words, the difference in the frequency detected versus the source frequency. Let's move this down. So I'm going to use the Doppler effect. Frequency detected equals frequency of the source, V plus Vd over V minus Vs. My source is at rest. But what's different here? This is dealing with a microwave, and a microwave is a form of electromagnetic radiation which all travels at the speed of light. So this V right here is equal to the speed of light. 3 times 10 to the 8th meters per second. If you think about it, you're not hearing anything when a radar gun is used. So because you're not hearing anything, you're not dealing with sound waves, so that's why we don't want to use the 343 meters per second. Doppler effect is still going to work the same exact way. With light waves, we're just changing what that value is. So frequency detected equals 10.5 times 10 to the 9th hertz times 3 times 10 to the 8th meters per second plus 20 meters per second over 3 times 10 to the 8th meters per second. This comes out to, and I'm going to write the whole number, 10.500007 times 10 to the 9th hertz. So similar, but not exactly the same. How do you figure out the beat frequency? You're going to take the absolute value, F1 minus F2. So that equals the absolute value of 10.5 times 10 to the 9th hertz minus 10.5, I'm just going to do the dot, 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 because it does keep going, times 10 to the 9th hertz. Subtracting those, this comes out to 700 hertz. So the detected beat frequency is 700 hertz. So the way radar guns actually work, each frequency will have a speed associated with it, and honestly all they did was really use the Doppler effect to figure out what that was. So in other words, a car moving at 20 meters per second would have a frequency of 700 hertz, so you would know if they were going greater than 20 meters per second, then your frequency would be greater. So that's how the radar guns work. They use tuning forks that are tuned to certain frequencies that associate with speeds. This is about as complicated as beats would get. The main idea, again, is that a beat is just the two frequencies very close together, and you're looking at the difference in the two frequencies.